Hello everyone, welcome to our daily session, learning sessions with Next Minds Academy. We offer classes online. We normally use Zoom for our classes. We also offer inquiry lessons and we offer free notes at our website, which is www.nextmindsacademy.com as shown down there. And also register with us, or you can contact us through our WhatsApp number, which is shown on our screen there. We shall be able to help you. Thank you. In our series of today's lesson, we are continuing with electricity discussion. Today, we're basically going to deal with section B questions of electricity. Let's look at the first question, which is here, and they're asking us to define a volt. So we all know that a volt is a measure of potential difference, and we know that potential difference is the work done. Potential difference in itself may be potential difference for it. It is measured in volts, and it is the work done moving 1 coulomb of charge from one point to another across a conductor. So current only flows when there is a potential difference between ends of the conductor. So when defining a volt, since it is a measure of potential difference, so we define it as a potential difference because of course it measures potential difference. So in the definition, we have to show that it is a potential difference. So, but where is it? It is between 2 points. It is between 2 points when 1 joule of work transferring 1 coulomb, transferring 1 coulomb of charge from one point to another. 1 coulomb of charge from one point to another. So in this definition of a coulomb, basically we have to involve some keywords. As you can see, there are some keywords like a potential difference. This is a keyword in the definition. Then 1 joule of work is also a keyword in the definition. Never forget it. And then 1 coulomb of charge from one point to another. Okay, so the second question, they are telling us to define electrical resistance. So we all know that electrical resistance is defined as the opposition to the flow, to the conduction or the flow of current. Is the opposition to the conduction or flow of current, to the flow of current in the conductor. So if you don't say that, you can also say it is the opposition of a conductor to the flow of current. So all the two are definitions for electrical resistance. Then the next question, we have a circuit here. The circuit, you can see how it is. It is made up or how it is arranged. So we have a source which is a battery of EMF 2 volts connected to this resistor of 2 ohms, which is in series with these two which are in parallel. So the 3 ohms resistor and the 2 ohms resistor, for them, they are in parallel, but the two, when you combine them, they are in series with the 2 ohms resistor. So they're asking us, or they are telling us that a battery of EMF 2 volts and negligible internal resistance is connected as shown in the figure above. Find the reading of the ammeter A. So we are required to find the reading of this ammeter. So first of all, before we find the reading of the ammeter, because the ammeter reads the current which passes through the 2 ohms resistor, through this resistor here. So, but to find it, we have to first find that current, we have to first find the PD which passes through this parallel combination. And also we need to find the current which passes through the whole system. So meaning that we shall first calculate the current through the system, or let's first calculate the total resistance in the whole system, starting with the parallel combination. So if I start with the parallel combination only, the resistance in the parallel combination will be given by, since there are 2, we shall use product over sum. So we shall use 2 times 3 out of 2 plus 3. And this will end up giving 5 out of 6. 6 out of 5. And this is similar to 1.2 ohms. So this means that the effective resistance in the entire circuit will be given by 2 ohms, which is in series with these 2 combined. So it will be 2 plus 1.2, and this will be 3.2 ohms. Okay, so we can go ahead, since the cell here has negligible internal resistance, so it's equivalent to 0. So you can go ahead and look for the current through the whole circuit. So for current, we shall use the formula. V is given by I multiplied by R. We've already found R. V is the voltage, which is 2 volts. So 2 is equivalent by I that we are looking for, multiplied by R, which we've got as 3.2 ohms. So finally, if you divide, you have I as being equivalent to 2 out of 3.2 amperes, and this one is actually equivalent to 0.625. If you press the calculator, this is 0.625 amperes. Okay, so after finding this is the current through the whole circuit. So meaning that the current which passes through this resistor here is 0.625 amperes, and the current through these two combined is also 0. The combination of these two also passes a current of 0.625 amperes. So we can now look for the PD which passes through the parallel combination, since resistors in series have different values of V, but V will be the same for this and this. So to find that value of potential difference, we shall use V equals IR. We are going to use this combined resistance, since the voltage is the same in parallel combination. So we shall end up having V being equivalent to 0.625 multiplied by 1.2. And finally, the V, which is in the parallel combination, will be given by 0.75 volts. So that means that the potential difference which passes through this parallel combination is 0.75. Potential difference through this 2 ohms resistor here is 0.75 volts. Even the potential difference through this 3 ohms resistor is 0.75 volts. So if we go ahead and we calculate the current through the 2 ohms resistor, which is the ammeter reading A, since we already have V and we have R, that current I will be given by V divided by R, but through the 2 ohms resistor, the V is 0.75 and its resistance is 2 ohms. So finally, that current will be equivalent to 0.375 amperes. So the ammeter reading in this case will be given by, or it will be equivalent to 0.75 amperes. 0.375 amperes, or 0.75 divided by 2 amperes. Okay, we have another question which asks us to define the following, stating their units. Starting with current, we define current as the rate of flow of electric charge. It's the rate of flow of electric charge. So when defining current, we define it as the rate of flow of electric charge. Mathematically, current can be given as charge divided by time. So the word rate in the definition involves time, and charge is already there. So we know that charge is measured in coulombs and time is measured in seconds. So meaning that current can also be measured in coulombs per second, though these are not the SI, this is not the SI unit for current. So the SI unit for current is what we call, the SI unit for current is amperes, or we write it as capital A, amperes, the SI unit of current. So meaning that 1 ampere, 1 A is equivalent to 1 coulomb per second. Okay, so next we are supposed to define power. Power, since we are dealing with electricity, it means that we shall be defining power, and we define it as electric power is the rate of doing work by an electric current. Rate of doing work by an electric current. So from here, or from the same definition, if we are to put power mathematically, of course, power will be given by the work done, the electrical work done divided by the time taken. We know that the electrical work done is given by IVT or VIT divided by, power will be IVT divided by time, where IVT is the work done or electrical work done. So meaning that power is given by IV. So power can also be written as, or it can also be expressed in other terms as I squared R, which can also be expressed as V squared out of R. So all these definitions can be used to, all these equations can be used to calculate power. So the SI unit of power is what we call watts, and we normally use a W for watts. Okay, so next we have a question here, and in this question here, they're asking us, or they're telling us that 3 identical lamps are connected as shown above. What is the reading of the voltmeter? So before we take the reading, you can see that all these lamps here are arranged in what we call a series arrangement. They are in series. So when lamps are in series, they all pass the same current. The current is the same because they are in series. It is only the potential difference, or what we can call voltage, which is different. Voltage is different, but current is the same. So since they are identical, it means that this voltmeter, because it is connected across this lamp here, it only measures the potential difference of this across this lamp that is passing through this lamp. Since all these 3 are identical, it means that they will share the 3 volts which are supplied equally. So meaning that these 3 volts here will divide itself equally among these 3 bulbs. So meaning that when we are looking for the reading of the voltmeter, it will be given by 3 volts divided by 3, and the voltmeter reading will basically be 1 volt, since they are identical and each has its own voltage that it passes, but the bulbs are identical. Okay, next question is stating Ohm's law. So for Ohm's law, for it, to state it, we state it as, or it is stated as, it basically relates current and potential difference. So it states that the current which is through a conductor or a wire, actually let me use a wire, current through a wire at constant temperature, directly proportional to the potential difference across the ends. Proportional to the potential difference the ends. Of course, the ends are for a wire or a conductor. So this statement here is the statement for Ohm's law. So when stating it, this word current is important. This constant temperature is very important because this is one of the conditions, and then the direct proportionality with the potential difference. So I'm underlining the keywords which should always be stated whenever we are stating Ohm's law. So part B, we have a question here which says that an ammeter connected in series with a cell and a 2 ohms resistor reads this when connected with a 2 ohms resistor. So meaning that if I'm to draw a simple circuit, maybe that means it is arranged somehow like this. Maybe if this is the ammeter, because there also maybe has to be a source of EMF, maybe like this. So when this is 2 ohms, this is 0.5 amperes, and when we replace the resistor with 5 ohms, the reading of the ammeter is 0.25 amperes. So they are asking us to calculate the internal resistance of the cell. So if the cell has an internal resistance, this is an external resistance. So meaning in our calculations, we are going to use the formula E equals to I into R plus R, where small r is the internal resistance and capital R is the external resistance due to an external resistor. This is the internal resistance of any of the appliances. So using this formula with 2 ohms and 0.5 ohms, if I use it with this and this, with a resistor of 2 ohms, and the ammeter reading as 0.5 amperes, the equation I get is E equals 0.5 into R plus 2. So if I call this equation 1, I can go ahead now and use the 5 ohms resistor with a reading of 0.25. So if I use that, I'll end up getting the equation as E equals, this is 0.25 into R plus 5. So we can solve these two equations to get the internal resistance, equation 1 and 2, to get the internal resistance, small r, and also get the EMF which is supplied by the cell. So solve this simultaneously. I want to eliminate r, so I'll multiply equation 2 by 1, and then after I'll subtract 2 into equation 2. I subtract equation 1. So meaning that I'll have 2e minus e, that will be e, and then 2 times 0.25, that is 0.5r, minus 0.5r, that is 0. So meaning that I'll have e as being equivalent to 0.25 times this. This is basically this will end up giving me 1.25 minus 1. It will end up giving me because 2 times 0.25, that is 0.5 times 5, that is 1.25. 1.25 minus 1, That gives me the value 1.25 minus 1. Is it 1.25 or 2.25? Okay. So finally, we end up having E as being equivalent to 2 times 0.25. Maybe I can do it here. Times 0.5 times 0.5. Everything we subtract 0.5 times 2. Subtract 0.5 times 2. So when you subtract this, you end up getting E as being equivalent to 1.5 volts. E being equivalent to 1.5 volts. Okay. So if we are to calculate R, the value of R, meaning we shall substitute E in one of these two equations. To calculate R, substitute the value of E in one of these two equations. So if we substitute it in any of those two equations, I'm sure you end up getting R, the internal resistance, as being equivalent to 1 ohm. So, but basically the major idea here is that we've solved these two equations simultaneously to find the value of E and the value of the internal resistance. So I think you can see part 2 wanted us to find the EMF of the cell, which we've got as 1.5 volts. And we've also found the internal resistance as 1 ohm by solving the equations simultaneously. Next question asks us that an appliance is rated 240 volts and 60 watts. So the 240 here is of course the PDF, and then the 60 is the power. 240 is PDF and 60 is the power. So when explaining what this means or how you understand by the statement, in your mind you should have that this is PDF and this is power. So when writing this, maybe we can explain it as when the lamp is connected to a 240 volts main, that is the source of EMF. When it is 240 volts, it produces 60 joules per second. Produces a power of 60 joules per second. Because this is power, which is work out of time, work done over time taken, which is the 60 joules per second. So basically that is simple how we can simply explain that one. Part B says, calculate the current flowing through and the resistance of the appliance when the appliance operated at the rated values. So of course, to calculate this, we are going to use the formula because power is given by IV, and we are already given power as 60 watts and V as 240 volts. So we can go ahead and calculate current as power divided by V, and this will be given by power, which is 60 divided by 240. So this equation will give you the answer for current, which will be in amperes. So 60 divided by 240, I think it gives around 0.25 amperes. So you can still go ahead and calculate the resistance. For resistance, we shall use V equals IR. And we already have V and we already have I. So meaning that R will be given by V divided by I. And this will be 240 divided by I, which is 0.25. And then you get the answer for the resistance. So we get 240 and divide by 0.25 and get the answer in ohms. Okay, otherwise, thank you for attending with us. Keep tuned for our next series of lessons. Have a blessed time.